A flash brighter than the sun vanishes in a millisecond. This is the enigma of a fast radio burst, an explosion of energy from the far reaches of space. For nearly 2 decades, these intense, fleeting signals have defied explanation, standing as one of the most profound puzzles in modern astronomy. They are not the steady glow of stars, but violent, cosmic lightning strikes, each one a brief shout across billions of light years. The central question is as simple as it is staggering. What kind of cosmic engine could possibly unleash so much power in the blink of an eye? By the end of this exploration, you will understand the leading suspects in this high-stakes astronomical investigation, from the corpses of dead stars to the edges of black holes. We are hunting for the most extreme engines in the universe, objects that bend the very laws of physics to their will. What do you think it takes to make the cosmos scream? The answer to that question began with a single, lonely data point. In 2007, a young astronomer named Duncan Lorimer was sifting through old observations from the Parkes radio telescope in Australia. He wasn't looking for anything revolutionary, just analyzing archived sky surveys. But buried in that mountain of digital noise was a spike, a signal so bizarre it stood out like a scream in a library. It lasted just 5 milliseconds, a flicker of time shorter than a camera flash. Yet in that instant, it released more energy than our sun does in an entire month. This was the first recognized fast radio burst, now known as the Lorimer Burst. Its properties were immediately shocking. The signal was stretched or dispersed across different radio frequencies. Think of it like a prism bending light, but here, the effect was caused by the signal plowing through clouds of ionized gas in space. The amount of stretching was immense, far greater than anything from within our own galaxy. This was the key clue. It meant the signal had traveled across an almost unimaginable gulf, billions of light years from far beyond the Milky Way. Here was a millisecond flash, brighter than whole galaxies, coming from the cosmic deep. The discovery was met with understandable caution. Could it be a glitch, some piece of earthly interference, or a malfunction of the telescope itself? The scientific community needed more evidence, a pattern to prove this wasn't just a cosmic one-off. That proof arrived slowly, then all at once. Over the following years, a handful of similar bursts were found, again in old data. Each one was a solitary, brilliant event with that same telltale dispersion from deep space. The reality became undeniable. Fast radio bursts were not anomalies, they were a new class of astronomical phenomenon. The universe, it seemed, was punctuated by these sudden, violent whispers. With their existence confirmed, the real mystery truly began. What out there, in the dark between galaxies, was capable of such focused, catastrophic power? The hunt for the engine was on. These fleeting cosmic events left astronomers with a distinct set of fingerprints. To identify the culprit, you first need to understand the crime scene. Every fast radio burst carries a specific profile, a list of extreme properties that any potential source must be capable of producing. The first and most obvious clue is the timescale. We are talking about events that are over in a flash, literally. They last mere milliseconds. That is not just fast, that is faster than the blink of an eye. This immediately tells us the engine itself must be incredibly compact. Why? Because nothing can travel faster than light. If an object were, say, the size of a star, a signal generated on one side would take noticeable time to reach the other. An event that bright and that brief must originate from a region no larger than a few hundred kilometers across, something roughly the size of a city. So we are hunting for something very, very small and unbelievably dense. Then there is the energy. This is the part that truly bends the mind. In those few thousandths of a second, A single fast radio burst can release as much energy as our sun does over several days or even months. Think about that for a moment. Our sun is a continuous nuclear fusion reactor, a vast sphere of churning plasma. To match its output, you would need to detonate billions of the most powerful nuclear weapons we have ever built, and then focus all that energy into a single, coherent beam of radio waves. The source must be an engine of almost incomprehensible efficiency and power. The radio signal itself holds further secrets. As it travels across the universe, it interacts with the thin soup of charged particles that fills the space between galaxies. This stretches the signal, delaying lower-frequency radio waves more than higher ones. Scientists measure this as dispersion. The immense dispersion of these bursts confirms they come from other galaxies, having traversed billions of light years. Some bursts also show a twisted, spiraling pattern called Faraday rotation. This is a smoking gun indicating the signal passed through an intensely magnetized environment, a region of space dominated by powerful magnetic fields. So the engine likely lies within or creates a zone of extreme magnetism. Perhaps the most critical clue of all came from an observatory in Canada. For years, every detected burst was a one-off event, a single brilliant flash and then eternal silence from that patch of sky. This suggested a catastrophic, destructive source. But then, one source did the unexpected. It flashed again and again. Astronomers found a repeater, a cosmic lighthouse that would fire off bursts intermittently, sometimes in frantic clusters, sometimes after long periods of quiet. This changed everything. It meant the engine could survive its own outburst. Whatever was powering these events was not necessarily destroyed in the process. This single distinction between one-off bursts and repeating sources became the most important filter for theories. It meant the universe might contain not one, but two different types of these extreme engines, or perhaps one engine operating in two different modes. The stage was now set. With this profile in hand, the investigation could truly begin, turning from mere observation to the high-stakes process of building and breaking cosmic alibis. The discovery of a repeater was the moment the mystery split in two. Before that, every theory had to explain a single, catastrophic event. Astronomers naturally looked to the most violent endings in the cosmos, the final, explosive deaths of stars. A massive supernova, for instance, or the spectacular collision of two ultra-dense neutron stars. These are universe-shaking events, capable of unleashing titanic energy. They were perfect suspects for the one-off bursts, but then a source flashed a second time, and that changed everything. If a supernova is the final, destructive explosion of a star, it cannot happen twice. A star only dies once. Similarly, if two neutron stars spiral together and merge in a blaze of gravitational waves, that is a single, terminal event. They are gone, consumed in the merger. A repeater immediately ruled out these kinds of one-time cataclysms for that specific source. The engine had to survive its own outburst. This was a pivotal fork in the road, forcing scientists to consider two distinct families of cosmic engines. On one path, you still have the true one-offs, the cosmic fireworks that represent a single, irreversible detonation. Their power source is spent in the event itself. On the other path, you now have the repeaters. These point to something persistent, a celestial machine that can build up energy, release it in a furious flash, and then somehow reset itself to do it all over again. It suggested an engine that was not destroyed but stressed, an object living on the edge of stability. This distinction became the most important filter for all the theories that followed. It meant the universe was not just screaming, it was sometimes screaming the same name over and over from the same dark corner of space. So what kind of object can walk that razor's edge, holding enough destructive power to outshine galaxies, yet stable enough to survive its own fury? The search now narrowed to the most resilient and volatile objects astronomers could conceive. To find an engine that can both explode and survive, you must look to the dead. Not all stellar corpses are quiet. When a massive star dies in a supernova, its core can collapse into a neutron star, a city-sized ball of matter so dense a single teaspoon would weigh as much as a mountain. Most neutron stars spin rapidly and possess powerful magnetic fields, but there exists an even more extreme variant. Imagine taking the magnetic field of a typical neutron star and cranking its strength up 1,000 times over. You get a magnetar, a celestial object with a magnetic field so intense it warps the very structure of matter around it. These fields are quadrillions of times stronger than Earth's, creating an environment of unimaginable stress. The star's rigid crust under this titanic magnetic strain can fracture. This is a starquake, a seismic event on a neutron star, where the crust shifts and snaps like a tectonic plate under impossible pressure. Alternatively, the magnetic field lines themselves, which are frozen into the star's superfluid interior, can become twisted and tangled. When they suddenly snap and reconfigure in an event called magnetic reconnection, they release catastrophic amounts of energy. Both of these processes, a crustal starquake or a magnetic snap, could channel vast energy into a focused beam of radio waves. Crucially, a magnetar could survive such an event. It would be shaken, its magnetic field rearranged but not destroyed. This made it the perfect theoretical candidate for a repeating fast radio burst engine, a stressed, volatile object that could fire again and again. For years, it was a compelling idea, but it needed proof. Then, in April 2020, the universe provided a clue from our own cosmic backyard. A known magnetar within the Milky Way, named SGR 1935+215, entered an unusually active phase, and from its direction, astronomers detected something unprecedented, a millisecond radio burst. This was not as powerful as the extragalactic fast radio bursts, but its properties were a perfect match in miniature. For the first time, an fast radio burst-like signal was caught emerging from a specific, identified object, a magnetar. It was the smoking gun, the direct observational link scientists had been hoping for. This landmark detection proved that magnetars are indeed capable of producing these brilliant millisecond flashes. Yet it also raised a new question. The burst from our galactic magnetar was thousands of times weaker than those coming from other galaxies. If magnetars are the engines, then the ones powering the most distant fast radio bursts must be in a state of hyperdrive, operating at intensities we have yet to witness up close. The case was compelling, but was it closed? Could this one type of stellar corpse explain every single flash in the cosmic dark? The magnetar offers a compelling blueprint for cosmic violence. To understand how it works, we need to peer inside this city-sized engine. Picture a sphere of unimaginable density, its surface a crust of iron nuclei locked in a rigid lattice harder than any diamond. Beneath this crust churns a superfluid sea of neutrons, and lacing through it all is a magnetic field of almost impossible strength. This field is not a passive feature, it is a dynamic, living force under immense tension. It is constantly trying to rearrange itself, to snap into a lower energy state, but it is frozen into the star's superfluid interior. Over time, as the star spins and its interior subtly shifts, these magnetic field lines become twisted and strained, like rubber bands wound tighter and tighter. There are two primary ways this pent-up energy can catastrophically release. The first is through the crust itself. The titanic magnetic stress can physically warp and fracture the neutron star's rigid surface. This is a starquake, a seismic event on a scale we cannot fathom, where entire sections of crust, kilometers thick, suddenly shift. The energy released is staggering, equivalent to hundreds of millions of our most powerful earthquakes concentrated into a single point. The second pathway is even more direct. Those wound-up magnetic field lines in the magnetosphere, the region of space dominated by the star's magnetism, can suddenly snap and reconnect. In a violent process called magnetic reconnection, the lines break and reform in a simpler configuration. This conversion of magnetic energy is explosively efficient, accelerating electrons and other particles to nearly the speed of light in an instant. But how does a crustal snap or a magnetic rearrangement in near-empty space create a brilliant flash of radio waves light-years away? The key is what happens next. Both of these eruptions, whether from the surface or the magnetosphere, blast out a wave of energy and ultra-fast particles. This creates a relativistic shock wave, a wall of plasma moving at a significant fraction of light speed. This shock wave then plows into the material surrounding the magnetar, often a cloud of debris left over from the star's explosive birth. Inside this turbulent collision zone, the shock wave forces electrons to spiral wildly along the magnetic field lines. This organized, frenetic motion is what generates the coherent beam of radio waves we eventually detect. It is like a cosmic natural laser, or maser, where the extreme conditions of the shock wave and the magnetic field orchestrate the radio emission into a powerful, focused signal. So the sequence is this: immense magnetic stress builds, the crust cracks or the field lines snap, a relativistic shock is born. It collides with surrounding debris, and from that chaos emerges a perfectly timed, coherent radio scream. This model explains not just the raw power, but the incredible brevity and focus of the burst. The entire chain reaction, from trigger to emission, is confined by the speed of light to a region only a few hundred kilometers across, lasting just milliseconds. It is a testament to an engine operating at the very limits of physical law. Yet this elegant model of a magnetar's fury faces a monumental challenge, one of sheer scale. The burst detected from our own galaxy's magnetar was a powerful event, but it was also a whisper compared to the cosmic shouts we hear from other galaxies. The most energetic extragalactic fast radio bursts are thousands, sometimes even millions of times more luminous. So the pressing question becomes, can a stellar corpse, even one as extreme as a magnetar, truly be responsible for the most brilliant flashes in the universe? To answer that, we must confront the physics of distance and energy. The signal from a distant burst has traveled for billions of years, spreading out in a vast, ever-expanding sphere. By the time that faint whisper reaches our telescopes, the energy that originally created it must have been almost beyond calculation. For the most powerful events on record, the energy requirement is staggering. In a single millisecond, the engine must release the equivalent of our sun's total output over several decades, all focused into a tight beam of radio waves. Could a magnetar's crust or magnetic field possibly store and release that much energy? The numbers push the limits of what we believe is physically possible for such an object. It is like comparing the crack of a whip to the detonation of a nuclear bomb. They are both sudden releases of energy, but the scale is incomparable. So if magnetars are the engines, they must come in a far more potent variety. One proposed solution is the existence of supermagnetars, newborn neutron stars with magnetic fields 100 times stronger still, and spinning at incredible speeds, nearly tearing themselves apart. Such an object, formed in the chaotic aftermath of a particularly violent supernova, would be a cosmic powerhouse, its magnetic reservoir deep enough to fuel those titanic bursts. There is another, equally critical factor that could resolve this energy crisis, a trick of geometry called beaming. We might not be seeing the true total energy of the burst, but rather a concentrated fraction of it. Imagine a lighthouse. Its lamp shines in all directions, but it uses a focused lens to direct that light into a single, sweeping beam. From the perspective of a ship in the path of that beam, the lighthouse appears intensely bright. But from any other angle, it is dark. The same principle could apply to a fast radio burst engine. If the radio emission is not sprayed in all directions, but is instead focused into an incredibly narrow jet, like a cosmic blowtorch, then the energy required drops dramatically. We are not seeing the full output of the engine, only the intense, narrow slice of it that happens to be pointed directly at Earth. This beaming effect could make a Magnetar-powered burst appear far brighter to us than its total energy would suggest, neatly bridging the gap between what we see in our galaxy and what we detect from the far reaches of space. So the Magnetar model survives this challenge, but it must adapt, proposing either engines of unprecedented ferocity or relying on a fortunate alignment in the dark. But Magnetars, for all their fury, cannot explain every flash. Remember that critical fork in the road, the distinction between repeaters and one-off events. For the bursts that have only ever been heard once, astronomers must consider engines that do not survive their own power. They look to the ultimate cosmic finales, events of such conclusive violence that they can only happen one time. This leads us to a second prime suspect, a collision of unimaginable density. Picture two city-sized stars, each one a neutron star, locked in a fatal gravitational embrace. They are the remnants of massive stars that lived and died as binary partners. Over eons, they spiral closer and closer, their orbit decaying as they radiate energy away in the form of gravitational waves, ripples in the fabric of space-time itself. This dance can last for millions of years, but its final act is over in less than a second. When they finally meet, they do not simply bump together. They coalesce in a cataclysm that shakes the universe. The moment of merger is a storm of physics at its most extreme. The two ultra-dense cores smash into one another, spinning at a significant fraction of light speed. For a brief, unstable moment, they may form a single, hyper-massive neutron star, an object so heavy and hot it pushes against the absolute limits of how much matter can be supported against its own gravity. This object is a fleeting phantom, existing for perhaps only a few hundred milliseconds before its own weight becomes too much to bear. It then undergoes a catastrophic collapse, its structure failing as it implodes to form a black hole. It is in these final, violent moments that theorists believe a fast radio burst could be born. The process is a cascade of unbelievable energy. As the two stars merge, powerful magnetic fields, trillions of times stronger than Earth's, are amplified and twisted in the turbulent maelstrom. Jets of material may be launched from the poles of the short-lived hypermassive star at nearly the speed of light. Alternatively, the very act of collapse, as the remnant neutron star gives way to a black hole, could trigger a final, desperate release of energy stored in its rotation and magnetism. In either scenario, the conditions are perfect for a relativistic shockwave, similar to the one around a Magnetar but born from a collision of worlds. This shock plows through the cloud of debris ejected during the merger, and in that chaotic, magnetized environment, a coherent beam of radio waves is generated. The signal would be a single, brilliant shout, a one-time event tied to a terminal cosmic transformation. After the flash, the hypermassive star is gone, having either collapsed into a black hole or settled into a more stable but silent neutron star. The engine is spent, the event unrepeatable. This model elegantly explains the non-repeating fast radio bursts, offering a direct link between these mysterious radio flashes and one of the most energetic events we know of in the cosmos, a neutron-star merger. It is a theory that connects two great mysteries of modern astronomy, suggesting that the same event that shakes space-time with gravitational waves might also, in its final instant, light up the radio sky with a fleeting farewell message. The gravitational wave revolution gave us a new way to listen to the cosmos. In August 2017, observatories named LIGO and Virgo felt the space-time ripples from a collision of two neutron stars over 100 million light-years away. This was a monumental detection, confirming a long-held theory and opening a new window on the universe. It was exactly the kind of cataclysmic merger that could, in theory, power a one-off fast radio burst. The astronomical community watched the sky in that direction with every instrument available, from gamma-ray telescopes to radio arrays. They found a brilliant afterglow, a kilonova, but no accompanying fast radio burst was detected. This absence is not a dismissal of the merger theory, but a crucial clue about its mechanics. It tells us that if a merger does produce a radio flash, the conditions must be just right for us to see it. The first and most likely reason we missed it is beaming. The radio signal from such an event is probably not a sphere of energy expanding in all directions. It is far more likely to be a narrow, focused jet, like a lighthouse beam sweeping through the darkness of space. For us to detect it, that incredibly precise beam must be pointed directly at Earth at the exact moment of the merger. Given the vastness of space and the random orientations of these collisions, the odds are that most of these cosmic flashes are pointing elsewhere, their brilliant light sweeping past us unseen. We are listening for a whisper in a hurricane, and we must be in the exact path of the shout to hear it. There is another, more physical barrier. The environment around a neutron star merger is unimaginably dense and violent. In the moments after collision, a vast cloud of hot, ionized debris expands outward. This material can be so thick with charged particles that it acts like a cosmic fog, absorbing and scattering radio waves before they can escape. For a fast radio burst to be born, the relativistic shockwave must punch through this cloud and emerge into clearer space, where it can generate the radio signal we can detect. If the cloud is too dense or if the shock is too weak, the radio flash is simply smothered at its source, trapped inside the aftermath of the merger. This suggests that only a specific subset of neutron star mergers possess the right conditions, the perfect balance of magnetic field strength, jet power, and debris density to produce a detectable radio signal. So the lack of a coincident detection does not rule out mergers as engines. Instead, it refines our search. It tells us we are looking for a rare alignment, both in the geometry of the event and in the physics of its aftermath. The universe may be filled with these brilliant finales, but only a fortunate few announce themselves to us with a flash we can see. But what if the collision itself is not the end, but a violent beginning? This brings us to a third, elegant possibility that merges the previous two theories into one. In this scenario, the neutron star merger does not immediately produce a black hole or a single, silent flash. Instead, imagine the two dense cores crashing together and coalescing into something new, a supercharged stellar corpse. The result is a hyper-massive neutron star, an object so massive and spinning so fast it should, by all rights, instantly collapse. Yet for a brief, glorious window, perhaps lasting only seconds or minutes, it holds itself together through sheer centrifugal force and the exotic pressure of its own matter. This newborn object is not just any neutron star. It is born in a maelstrom of amplified magnetic fields and ferocious rotation, emerging as a magnetar of unprecedented power. This is an engine forged in the single most violent event we know, now alive and screaming into the cosmos. Its birth is the ultimate starquake, a birthquake on a scale that defies comprehension. The immense energies released as its magnetic field settles, its crust solidifies from a seething plasma, and its rotation gradually slows could power not one, but a series of catastrophic radio bursts. In this model, the merger is the trigger that creates the repeating source. The unstable, super-magnetized newborn star fires off frantic signals as it finds its footing, like a cosmic infant finding its voice through fits of energetic crying. This elegantly bridges the gap between one-off cataclysms and persistent repeaters. It suggests that some of the repeating signals we detect might not be from ancient, long-lived magnetars, but from incredibly young ones, mere moments old in cosmic terms, born from the ashes of a stellar collision. The repeating bursts would then be the death throes of an impossible star, the final flickers of a brilliant, doomed object fighting against its own inevitable gravity. As it spins down and its internal structure stabilizes, the bursts would become less frequent and then cease entirely. The engine might ultimately still collapse into a black hole, but not before announcing its spectacular birth with a series of brilliant radio shouts across the universe. This idea transforms our view of these events from a simple finale into a dynamic, multi-act drama of creation and destruction, all compressed into a heartbeat of cosmic time. Yet beyond the violent lives and deaths of stars lies an even more titanic class of cosmic engine. To find it, we must shift our gaze from stellar corpses to the gravitational hearts of galaxies themselves. At the center of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole, a monster millions or even billions of times heavier than our Sun. Most are quiet, dormant giants, but when they feed, they become the most luminous and powerful persistent objects in the universe. We call these active galactic nuclei, and their fury is channeled through jets that can stretch for thousands of light years. These are not gentle streams, but relativistic beams of plasma launched from the poles of the black hole's accretion disk at nearly the speed of light. The physics within these jets is a maelstrom of shocks, magnetic fields, and particles moving at such incredible speeds that they glow across the electromagnetic spectrum. Within this chaotic, magnetized environment, some theorists propose, could lie the mechanism for a fast radio burst. A sudden instability in the jet, a collision between different streams of material, or a magnetic reconnection event within the focused beam could, in principle, generate a coherent pulse of radio waves. The sheer scale of these jets means the energy budget is virtually unlimited, easily capable of powering even the most luminous bursts we observe from across the cosmos. This would place the source of some fast radio bursts in the most extreme environments we know, directly linking them to the engines that shape entire galaxies. There is an even more violent feeding scenario to consider. Occasionally, a star wanders too close to a dormant supermassive black hole. The immense tidal forces of the black hole stretch and shred the star in a cataclysmic event called a tidal disruption. As the stellar material is pulled into a swirling accretion disk before falling into the void, it heats to incredible temperatures, creating a brilliant flare of light. The sudden influx of matter could also trigger the launch of a temporary jet. In the chaotic aftermath of this stellar destruction, as the jet forms and interacts with the debris, conditions might be ripe for a one-time, catastrophic radio burst. This model offers a different kind of one-off engine, one not born from the collision of two dense objects, but from the complete annihilation of a star by a gravitational monster. These hypotheses are more speculative, venturing into the domain of the truly monstrous and the extraordinarily rare. But they remind us that to explain the most extreme flashes in the sky, we must be willing to consider all possibilities, even those that operate on the scale of galaxies themselves. The brilliance of a fast radio burst is only half the mystery. Its very nature presents a deeper, more fundamental puzzle that every theoretical engine must solve. It is not just a bright flash of radio waves, it is a coherent flash. This is a crucial distinction that separates these events from almost everything else we see in the cosmos. Most light and radio waves from space are what scientists call incoherent. Think of a bustling city at night, where every window has a light on, but each bulb switches on and off independently. The overall glow is bright, but it is chaotic, uncoordinated. That is like the radio emission from a pulsar or the sun, photons emitted by countless individual particles acting on their own. A coherent signal is the opposite. It is like a stadium full of people holding up colored cards, flipping them in perfect unison to create a single, massive image. Every radio wave is in lockstep with its peaks and troughs perfectly aligned. This coordination is what allows the signal to remain focused and incredibly bright across billions of light years, rather than fading into a diffuse whisper. So the central question becomes, how does the universe orchestrate such a perfect, synchronized radio scream in a fraction of a millisecond? The leading answer lies in a process known as a synchrotron maser. To understand this, picture the aftermath of a cosmic catastrophe, whether a Magnetar's starquake or a neutron star collision. A shock wave, a wall of energy and particles moving at nearly the speed of light, plows into a surrounding cloud of magnetized plasma. Inside this turbulent collision zone, electrons are whipped into a frenzy, forced to spiral at incredible speeds along the tangled magnetic field lines. Normally, these electrons would emit radio waves randomly, creating that familiar incoherent city light. But under these specific, extreme conditions, something remarkable happens. The radio waves being produced can actually stimulate the electrons to emit more waves, perfectly in phase with the original ones. It is a chain reaction of light, where one wave triggers the next, and that one triggers another, all perfectly synchronized. This is the maser effect, which stands for microwave amplification by stimulated emission of radiation. It is essentially a natural laser, but for radio frequencies. The shockwave and the magnetized plasma provide the perfect amplifier, taking the chaotic energy of a cosmic explosion and organizing it into a single, coherent, and devastatingly powerful beam. This mechanism is the unifying thread that weaves through all the competing theories. Whether the engine is a Magnetar's crust snapping, a neutron star merger's final gasp, or a black hole's jet hiccuping, they all must create the same essential environment, a relativistic shock plowing into a magnetized medium. Only then can the synchrotron maser ignite, transforming raw cosmic violence into the precise, luminous signal that crosses the universe to reach us. It is the universal translator that turns the chaos of a stellar death into a message we can finally begin to decode. But a brilliant engine in empty space would flash unseen. The final piece of this cosmic puzzle is not the trigger, but the stage upon which it performs. The environment surrounding the source is as critical as the source itself, acting as the amplifier and the lens that shapes the signal we eventually receive. Think of it this way: a lightning bolt in the open sky is a spectacular sight, but it is silent. Only when that lightning strikes the ground or interacts with the air around it do we hear the thunderclap. For a fast radio burst, the thunder is the radio signal, and it needs a specific kind of atmosphere to form. This environment is often the legacy of the engine's own violent past. A young Magnetar, for instance, is likely embedded within the expanding shell of its own supernova remnant, a cloud of gas and dust ejected when its parent star exploded. This nebula is not empty, it is a turbulent, magnetized fog of charged particles. Similarly, the aftermath of a neutron star merger is a swirling debris field of hot, dense material. These are not passive clouds, they are dynamic and structured. When the engine unleashes its energy, whether through a crustal quake or a magnetic reconnection, it sends a relativistic shockwave screaming outward. This shockwave is the lightning bolt, but for it to produce the coherent radio thunder we detect, it must slam into something. It needs a medium. The circumstellar environment provides that crucial target. As the shock plows into this dense, magnetized nebula or debris shell, it compresses and energizes the material, creating the perfect conditions for the synchrotron maser to ignite. The environment becomes the amplifier, taking the raw energy of the shock and organizing it into that focused, coherent beam. Variations in this surrounding material could explain the incredible diversity we see among fast radio burst sources. Why do some sources repeat while others do not? Perhaps a repeater lies inside a particularly rich and persistent nebula, a constant fuel source for its shocks. Each time the Magnetar's crust fractures, the new shockwave finds ample material to interact with, producing another brilliant flash. A one-off burst, on the other hand, might occur in a more sparse or temporary environment. Imagine a shockwave from a merger event expanding into a debris cloud that is itself rapidly dissipating. The first shock finds enough material to make a brilliant flash, but by the time the engine could theoretically fire again, the amplifier has vanished, leaving any subsequent outbursts silent and dark to our instruments. The properties of the environment could also sculpt the signal itself, influencing its brightness, its polarization, and even its detailed structure. A dense, clumpy nebula might produce a more complex burst profile, while a smoother shell could result in a cleaner, simpler pulse. So the search for the engine is also a search for its home. We are not just listening for a scream in the void, we are trying to understand the acoustics of the hall it is echoing through. Every brilliant flash is also a messenger. While we hunt for the engines that create fast radio bursts, the signals themselves are on an epic journey, traversing the vast emptiness between galaxies. That journey is not through a perfect vacuum, it is a passage through the thin, invisible fabric of the cosmos itself, and as the radio waves travel, they are subtly changed by everything they pass through. This means every burst carries a hidden imprint, a forensic record of the space between its source and us. Astronomers have realized that this is not just a problem to be corrected, it is an extraordinary opportunity. By reading these subtle distortions, we can use fast radio bursts as the most precise probes ever devised to map the universe's hidden architecture. The first and most telling clue is the signal's dispersion. You can hear this effect yourself. If you drop a stone into a still pond, the ripples spread out in perfect circles. But if you drop that stone into a stream, the current will stretch the ripples, distorting their shape. Something similar happens to a fast radio burst as it crosses the cosmos. Space is not entirely empty. It is filled with a tenuous fog of ionized gas, individual electrons stripped from their atoms. This material is the legacy of the Big Bang and the outflows from countless galaxies, a diffuse medium known as the intergalactic medium. When the burst's radio waves encounter these free electrons, they are slowed down, but not all frequencies are slowed equally. Lower frequency radio waves, like deeper musical notes, interact more strongly and are delayed more than the higher frequencies. By the time the signal reaches Earth, what was once a sharp, simultaneous pulse has been stretched into a descending chirp, with the highest notes arriving a fraction of a second before the lowest. The greater the stretch, the more electrons the signal has passed through, and therefore, the greater the distance it has traveled. This dispersion measure is our primary yardstick for gauging how far away a burst originated, placing it firmly in a distant galaxy. But it does more than that. By comparing the dispersion to the known distance of the burst's host galaxy, astronomers can calculate exactly how much material lies in the intervening space. Each burst becomes a single, piercing beam of light that illuminates the total amount of ionized matter along its specific path. By collecting signals from many different directions, we can begin to build a three-dimensional map of this cosmic fog, weighing the unseen material that makes up the cosmic web of filaments and voids. The signal holds another, more subtle fingerprint, a twist called Faraday rotation. This effect is caused by magnetism. If the radio waves pass through a region with a magnetic field, the orientation of their waves begins to slowly rotate, like a corkscrew turning as it moves forward. The stronger the magnetic field and the denser the plasma it is threaded through, the more pronounced the twist becomes. By measuring this rotation in a fast radio burst, scientists can detect and quantify magnetic fields in the most remote regions of the universe, places far from any star or galaxy. This is revolutionary. Cosmic magnetism is one of the great unsolved puzzles. We know magnetic fields exist within galaxies, but how did they get there? And do they also permeate the vast intergalactic voids? A single fast radio burst can act as a probe sent through these mysterious regions. The amount of Faraday rotation tells us about the strength and structure of any magnetic fields along its entire line of sight, from the immediate environment of the source, through its host galaxy, across the intergalactic wilderness, and finally through the halo of our own Milky Way. By untangling these different contributions, we can search for the faint imprint of a primordial magnetic field, one that might have been woven into the fabric of the universe in its earliest moments. This transforms our perspective entirely. Fast radio bursts are no longer merely cosmic anomalies to be explained. They have become precision tools for discovery. Each one is a flashbulb that illuminates the dark corridors of the cosmos. With enough of these flashes from enough different directions, we can begin to chart the invisible. We can weigh the missing ordinary matter that theories predict should exist but has eluded our telescopes. We can trace the magnetic fields that shape how galaxies form and how cosmic rays travel. The very phenomenon that baffled us for years is now offering a new way to see. The universe is using its most violent whispers to help us map its hidden bones. For years, the hunt for these cosmic flashes was a painstaking game of chance. Astronomers pointed giant, single-dish telescopes at tiny patches of sky, hoping a burst would just happen to go off in their narrow field of view. It was like trying to study lightning by staring through a soda straw. Then, in the forests of British Columbia, a new kind of eye opened on the universe. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, was not built to chase fast radio bursts. Its original mission was to map the vast cosmic web by detecting faint radio signals from distant hydrogen. But its design made it the perfect machine for a revolution. Unlike a traditional telescope that looks at one point, CHIME has no moving parts. It is a fixed array of 4 massive half-pipe cylinders, each one the length of a football field, lined with over 1,000 antennas. This gives it an enormous field of view, about 200 times the area of the full moon. Every day, as the Earth rotates, CHIME scans the entire northern sky. It is not a soda straw, it is a wide-angle lens on the cosmos, watching constantly for the briefest flickers of radio light. This change in perspective was transformative. Almost immediately, CHIME began detecting fast radio bursts at a rate that stunned the astronomical community. Where before we had catalogued a few dozen over a decade, CHIME now began finding them by the hundreds and then the thousands. The trickle of data became a flood. This statistical wealth changed everything. For the first time, astronomers could stop treating each burst as a unique, mysterious event and start seeing them as a population. They could classify them, look for patterns, and understand their demographics, just as a biologist might study a forest by counting different species of trees. One of CHIME's most critical contributions was in finding more repeaters. Before CHIME, only a handful of repeating sources were known, making them rare curiosities. With its constant monitoring, CHIME revealed that repeaters are far more common than we thought. It found sources that would erupt in frantic storms of activity, firing off dozens of bursts in a single day, and others that would remain silent for months before whispering again. This proved that repeating is not a bizarre exception, but a fundamental mode of behavior for a significant fraction of these engines. The sheer volume of data allowed scientists to ask new kinds of questions. Are the bursts from repeaters different from the one-offs? The answer appears to be yes. On average, repeating bursts are slightly less energetic and last a fraction longer than their one-time counterparts. Their signals also tend to show more complex structures with multiple peaks within a single millisecond flash. This suggests the engines behind them might be operating in a slightly different, perhaps less catastrophic regime. The population data from CHIME also began to paint a picture of where these bursts live. They are not confined to any special type of galaxy. They have been found in massive old galaxies, in tiny young dwarf galaxies, and in everything in between. This tells us the engine is a versatile one, capable of forming in a wide variety of cosmic environments. The era of CHIME has transformed fast radio burst science from a mystery hunt into a field of statistical astrophysics. We are no longer just asking what they are, we are beginning to understand how they live, how common they are, and how they fit into the life cycle of the universe. Each new detection is no longer just a puzzle, it is another data point in a grand cosmic census, helping us to finally hear the full story these flashes are trying to tell. A cosmic address is far more than just a point on a map. For a fast radio burst, its precise location is the key to unlocking its origin story. We can measure its energy and trace its journey through space, but to truly understand the engine, we must see the neighborhood it calls home. Which galaxy does it live in, and what is that galaxy like? This requires a different kind of telescope, one that can act as a cosmic surveyor. While wide-field instruments like CHIME are brilliant at discovering bursts, their resolution is like a wide-angle camera photo, showing a vast area but lacking fine detail. To pinpoint a burst to a single galaxy among millions, astronomers turn to the masters of precision, radio interferometers. These are not single dishes, but vast arrays of antennas spread across continents, working in unison. By combining signals from telescopes separated by thousands of kilometers, they create a virtual telescope with the resolution of a dish as wide as the distance between them. It is like having a microscope for the sky. When CHIME or another telescope detects a promising burst, especially a repeater, an alert goes out across the global network. Within hours, powerful arrays like the Very Long Baseline Array in the United States or the Australian Square Kilometre Array Pathfinder swing into action. They zoom in on the patch of sky, a region the size of a grain of sand held at arm's length, and listen. If the source repeats, these ultra-sensitive, high-resolution instruments can triangulate its position with astonishing accuracy, often narrowing it down to a specific region within a single, distant galaxy. This is the moment of revelation when a mysterious flash gains a cosmic context. The findings from this meticulous detective work have been profoundly surprising. There is no single type of fast radio burst neighborhood. The host galaxies are a study in cosmic diversity. Some bursts originate in massive, ancient galaxies, huge elliptical systems where the frenzy of star formation died out billions of years ago. These are quiet, settled places dominated by older, redder stars. In such an environment, the engine is likely something left over from the galaxy's more violent youth, a long-lived Magnetar wandering through a stellar graveyard. Other bursts, however, have been traced back to the opposite extreme, tiny, chaotic dwarf galaxies. These are modest in size but ferociously active, churning out new stars at a breakneck pace. Their interstellar gas is turbulent and rich, the perfect nursery for massive stars that live fast, die young, and leave behind powerful magnetars or the neutron star binaries that may one day merge. This diversity is a crucial clue. It strongly implies that we are not dealing with one single type of engine, but with multiple pathways to cosmic violence. The engine that thrives in a calm, old galaxy might be fundamentally different from one born in a star-forming frenzy. An ancient Magnetar, slowly building stress over eons, could explain a repeater in an elliptical galaxy. Meanwhile, the cataclysmic merger of two neutron stars, which requires a recent history of massive star formation, fits perfectly within a young, star-bursting dwarf. The galactic environment acts as a filter, telling us what kinds of stellar lives and deaths are possible there. By reading the address of each flash, we are starting to build a census, linking different types of bursts to the specific cosmic conditions that forge them. The map is being drawn, and it shows a universe where brilliant millisecond screams can arise from almost any corner, from the quietest retirement communities of stars to their most riotous nurseries. Distance alone can rewrite the rules of the game. In June of 2022, a radio telescope in Western Australia captured a signal that did exactly that. Designated Fast Radio Burst 2022-0610A, this event shattered all previous distance records. Its journey to Earth began when the universe itself was a mere 5 billion years old, barely a third of its current age. This was not a signal from a distant galaxy, but a message from the cosmic past, from an era when galaxies were still assembling themselves in a denser, more chaotic cosmos. The sheer scale of this distance forced a recalculation of everything we thought we knew about these engines. To appear as bright as it did to our telescopes after traveling for 8 billion years, the burst must have been unfathomably luminous at its source. The numbers are staggering. In that millisecond, it released more energy than our Sun will emit over 30 years. This level of output pushes every theoretical model to its breaking point. Could a Magnetar's crust hold that much stress? Could a neutron star merger channel that much energy into a radio beam? The existence of this single burst suggests that in the early universe, the engines behind these flashes were not just more common, but operating in a hypercharged state. The young cosmos was a different place, richer in the raw materials for creating stellar monsters. Star formation rates were far higher, meaning massive stars were born, lived, and died in frantic succession. This environment would have been a perfect factory for the most extreme stellar remnants, forging magnetars with stronger magnetic fields and neutron star binaries destined for swift, violent mergers. The detection of this ancient flash implies that such titanic engines were not rare anomalies, but perhaps a regular feature of that tumultuous epoch. It forces us to consider that the physics of these events might have been different under those early conditions, with denser surrounding material or more powerful magnetic fields amplifying the bursts to levels we rarely see in the quieter, more spread-out universe of today. This one signal from the deep past is a profound clue. It tells us that to truly understand fast radio bursts, we must look not only across space but back in time, to an era when the universe itself was young, violent, and capable of forging engines of almost unimaginable power. The rhythm of a repeating source holds its own secret language. For some of these cosmic lighthouses, the flashes do not come at random. They arrive in predictable windows, opening and closing with the precision of a celestial clock. This discovery of periodicity is perhaps the single most revealing clue about the geometry of the engine itself. It tells us we are not just watching an isolated object, but a dance. One of the first and most famous examples is a repeater known as Fast Radio Burst 180916, which was found to have a remarkable pattern. It would erupt in a storm of activity for about 4 days, firing off multiple bursts. Then it would fall completely silent for 12 days. After that 16-day cycle, it would switch on again, right on schedule. This was not a random hiccup, it was a heartbeat. Another source, Fast Radio Burst 121102, revealed an even longer rhythm, a grand cycle of approximately 157 days of activity followed by a long period of quiet. These patterns are a direct fingerprint of orbital motion. The most compelling explanation is that the engine, likely a magnetar, is not alone. It is locked in a binary system orbiting another object. This companion could be another neutron star, a black hole, or even a massive, bloated star. As the two objects swing around their common center of gravity, their orbital dance creates a regular cycle of favorable and unfavorable conditions for producing bursts. Think of it like a lighthouse on a rocky island with a second, larger island nearby. As the lighthouse orbits, there are times when its beam shines clearly out to sea, where our ship, Earth, can see it. Those are the active windows, but for much of its orbit, the beam is pointed away from us, blocked by the companion object, or shining into a void where conditions are not right to produce a signal we can detect. The geometry of the system acts as a cosmic shutter, periodically allowing us to see the flashes. The period of the cycle, those 16 or 157 days, directly tells us the orbital period of the system. This is a monumental constraint. It immediately rules out models where the engine is a solitary, wandering object. It forces the environment to be dynamic, shaped by the gravitational and possibly the magnetic influence of a companion. The presence of a nearby star, for instance, could provide a steady wind of material. As the Magnetar moves through this wind during specific phases of its orbit, the shock wave from its outbursts might find the dense fuel it needs to produce brilliant radio emission only at that precise point. Alternatively, the companion's gravity could periodically stress the Magnetar's crust, triggering quakes only when the two are closest together. The periodic windows are not just a curiosity, they are a diagnostic tool. By studying the length of the active window versus the silent period, astronomers can infer the eccentricity of the orbit, how elliptical it is. The stability of the cycle over years tells us about the long-term dynamics of the system. Each repeating burst from such a source is now a data point in a celestial mechanics experiment, allowing us to weigh the unseen companion and map the invisible architecture of this extreme binary partnership. The universe is not just screaming, it is screaming in time to a hidden gravitational music. The search for an engine pushes physics to its very limits. When the most extreme stellar corpses and collisions still struggle to explain the data, scientists must look beyond the known into the realm of the truly hypothetical. Here, in the domain of high theory, we find possibilities woven from the fabric of the cosmos itself. One such idea involves cosmic strings. These are not physical strings, but hypothetical one-dimensional defects in spacetime, thought to have formed in the universe's first chaotic moments after the Big Bang. Picture the fabric of reality cooling and settling, but in some places it develops a kink or a tear that becomes frozen in, a flaw in the cosmic crystal stretching across the universe. These filaments would be unimaginably thin, yet possess immense mass, vibrating like cosmic guitar strings. The theory suggests that if two such strings cross, or if a loop of string pinches off and decays, the event could convert its vast energy into a burst of radiation, potentially manifesting as a fast radio burst. It is an engine made not of matter but of space-time topology, a crack in reality healing itself with a brilliant flash. Another speculative candidate emerges from the hunt for dark matter. One proposed particle for this unseen substance is called the action. In certain models, these ultra-light particles could theoretically clump together under gravity to form action stars, diffuse balls of dark matter. While these stars would normally be invisible, a catastrophic interaction could make them briefly shine. If an action star were to pass through the magnetosphere of a neutron star, the intense magnetic field could trigger the actions to decay into photons, producing a sudden, intense burst of radio waves. Alternatively, if two action stars were to collide, they might annihilate in a flash of energy. These ideas are not mainstream and they lack direct observational support, but they are profoundly important. They demonstrate the sheer creative reach required by this mystery. Fast radio bursts are so extreme, so demanding of power, that they force physicists to consider every conceivable reservoir of energy in the universe, from the wreckage of stars to the architecture of spacetime and the nature of the dark cosmos itself. The phenomenon acts as a crucible for theory, testing our deepest ideas about what is possible. A brilliant radio flash is a single note in a cosmic symphony. To truly understand the orchestra, we must listen with more than one ear. This is the driving idea behind the search for multi-messenger counterparts, an ambitious global effort to catch a fast radio burst not just in radio waves, but across the entire spectrum of light and even with other, more exotic cosmic messengers. Imagine hearing a sudden, loud bang in a dark forest. Your ears tell you something explosive happened, but to know what it was, you desperately need to turn on a flashlight and see the source. For astronomers, the radio burst is that loud bang. Detecting a counterpart in optical light, X-rays or gamma rays would be that illuminating beam of light, revealing the engine's true nature and its broader impact on its surroundings. An X-ray counterpart, for instance, would signal the presence of searingly hot plasma or particles accelerated to near light speed. A simultaneous flash of visible light could point to a supernova-like fireball or a brilliant kilonova. Even the detection of a neutrino, an almost massless ghost particle that rarely interacts with matter, would be a revolutionary clue. Neutrinos are produced in the hearts of the most extreme events, like collapsing stellar cores or matter falling into black holes. Catching one from the direction of a fast radio burst would be a direct fingerprint of the engine's nuclear or gravitational furnace, telling us definitively that we are witnessing matter being utterly transformed. The scientific payoff would be transformative. A multi-wavelength detection would allow astronomers to measure the total energy budget of the event, not just the fraction channeled into radio waves. It would reveal the temperature, density, and chemical composition of the material involved. Most importantly, it would directly link the mysterious radio flash to a known class of astrophysical cataclysm, finally placing it on the familiar map of cosmic violence. Yet this search is one of the most formidable challenges in modern astronomy. The primary obstacle is time. These bursts last mere milliseconds, and their afterglows, if they exist at all, may fade in seconds or minutes. By the time a radio telescope detects a burst, processes the signal, and sends an automated alert to other observatories around the world, precious moments have already been lost. Pointing a large optical telescope or a space-based X-ray observatory is not like aiming a flashlight. It is a slow, mechanical ballet of massive instruments. The chance of swinging another telescope to the exact right spot in the sky before the light fades is vanishingly small. To overcome this, scientists have built rapid response networks. When a facility like CHIME identifies a burst, it instantly transmits its coordinates to a global alert system. Robotic optical telescopes, pre-programmed to respond without human intervention, immediately interrupt their scheduled observations and slew to the target. In space, missions like NASA's Neil Gehrels Swift Observatory, designed to study gamma-ray bursts, can pivot relatively quickly to search for X-ray afterglows. The strategy is to catch the echo of the explosion, the lingering heat from the shockwave as it expands and cools, while a direct hit, seeing the exact moment of the radio flash in another wavelength, remains the holy grail. Even a delayed afterglow detected minutes or hours later would be a monumental success. It would confirm that the event left a tangible thermal footprint, proving the burst was not just a coherent spike of radio energy, but a genuine astrophysical explosion that heated its environment. Every time a new fast radio burst is detected, this silent, global race against the clock begins anew. Telescopes across the planet and in orbit pivot and stare, hoping to catch a fading whisper of light that could turn a solitary radio scream into a full-throated cosmic chorus. The most active repeaters are not steady cosmic metronomes. Their behavior is erratic, a study in extremes that reveals the volatile nature of the engine within. Some sources will fall silent for months or even years, only to suddenly erupt in a frantic storm, firing off dozens of bursts in a single day. Others show a more predictable, almost seasonal pattern of activity, with windows of productivity followed by long stretches of quiet. This is not random noise, it is a language of stress and release, telling us how the engine stores and spends its catastrophic energy. Think of it like a geological fault line. Stress builds slowly, invisibly, as tectonic plates grind against one another. For long periods, the surface is calm. Then, without warning, the pressure exceeds a critical threshold, the fault slips, and the energy releases in a violent earthquake. After the main shock, aftershocks can continue for days or weeks as the system settles into a new, temporary equilibrium. A repeating fast radio burst source may operate on a similar principle, but with magnetic stress or crustal strain instead of rock. The long quiet periods are when the engine, likely a Magnetar, is winding up. Its magnetic field lines are being twisted, or its rigid crust is being deformed by unimaginable forces. This builds a reservoir of pent-up energy. The active storm, that cluster of bursts, represents the fault slipping. The initial burst might be the main shock, a large fracture in the star's crust, or a major reconnection of its magnetic field. The subsequent flurry of smaller bursts could be the aftershocks, as the crust continues to settle or the magnetic field relaxes into a new, slightly more stable configuration. Then the cycle begins again, a slow, invisible winding of the cosmic spring. This model suggests the engine has a finite, internal fuel source, the elastic energy stored in its own structure. Each burst depletes that reservoir a little until it needs time to recharge. But there is another possibility, one that requires an external fuel supply. If the Magnetar is in a binary system with a companion star, it might be continuously fed by a stream of gas. This process, called accretion, could provide a steady drip of material onto the neutron star's surface or into its magnetosphere. In this scenario, the bursts might be triggered by instabilities in this incoming flow. A clump of denser gas falls in, causing a localized spike in pressure that triggers a magnetic reconnection event or a small crustal crack. The bursting pattern would then follow the irregularity of the accretion stream, sometimes smooth and quiet, sometimes gushing and stormy. The changes we observe in a repeater's activity over years could reflect long-term shifts in this relationship. Perhaps the companion star itself is evolving, puffing up and providing more fuel, or the orbit is slowly decaying, bringing the two objects closer together and intensifying their interaction. By listening to the rhythm or lack of rhythm in these repeating shouts, we are essentially taking the engine's vital signs. Is its heart beating from internal stress, or is it being fed from an external drip? The answer changes not just what the object is, but how it lives and ultimately how it will die. The most profound clues often come not from the distant cosmos, but from our own celestial backyard. In April 2020, the universe offered a crucial piece of the puzzle from inside the Milky Way. A known Magnetar, catalogued as SGR 1935 plus 215, stirred from its slumber. This object, roughly 20,000 light-years away, entered a period of intense activity, emitting a storm of X-rays and gamma rays. Then, radio telescopes caught something unprecedented. From the precise direction of this Magnetar came a brilliant, millisecond-long burst of radio waves. It was not as powerful as the extragalactic fast radio bursts, but its profile was a perfect match in miniature. For the first time, a fast radio burst-like signal had been definitively traced to a specific, known object. This detection was the smoking gun, the direct evidence that Magnetars could indeed produce these fleeting radio screams. But the story did not end with that single, landmark flash. As astronomers continued to monitor this galactic Magnetar, they heard something else, a faint, rapid chattering beneath the main event. Alongside the rare, brighter bursts, the Magnetar was emitting a constant drizzle of much weaker radio pulses. These were not the universe-shaking shouts of an extragalactic fast radio burst. but something far quieter, which scientists began calling Nano-Fast radio bursts. The name is a bit of a misnomer, as these pulses are still immensely powerful, but they are millions of times fainter than their colossal cousins from other galaxies. This discovery was perhaps even more illuminating than the initial detection. It suggested that the engine does not operate in an all-or-nothing mode. Instead, it seems to have a volume knob. The Magnetar can produce a full spectrum of radio outbursts, from the faintest nano whispers to the occasional, more energetic millisecond shout. Studying our local Magnetar is like having a cosmic laboratory down the street. Astronomers can observe it with incredible detail across every wavelength, from radio to X-rays, watching the before, during, and after of each tiny eruption. They can see how a small starquake or a minor magnetic reconnection event correlates with a specific nanopulse. This allows them to dissect the burst mechanism in exquisite detail, confirming the models of shocks plowing into surrounding material. The existence of this continuum, from nanopulses to the galactic fast radio burst and up to the titanic extragalactic events, points to a unified physical origin. It implies that the difference between a faint pulse and a universe-spanning flash may not be a difference in kind, but a difference in scale and efficiency. Perhaps it comes down to the amount of energy stored and released in a single event, the density of the surrounding material the shockwave hits, or the precise alignment of the beam. Our galactic neighbor demonstrates that the fundamental engine, the stressed Magnetar, is capable of it all. It tells us that the cosmos is filled with these stressed objects, some whispering, some shouting, and a few, under the perfect storm of conditions, unleashing a scream so loud it can be heard from the dawn of time. The sheer power of these bursts naturally led to some extraordinary early theories. When a signal arrives from deep space, carrying immense energy in a structured, coherent pulse, one of the first questions asked is whether we are seeing something intentional. Could these be the signatures of an advanced civilization, perhaps using unimaginable technology to communicate or propel spacecraft across the void? It is a compelling idea from science fiction, but the scientific evidence has firmly steered us elsewhere. The primary reason is the sheer, wasteful scale of the phenomenon. For a civilization to generate a signal detectable across billions of light years, it would need to harness the total energy output of a star, focusing it into a millisecond radio blast. This is not an efficient way to send a message. It is a cosmic flare gun, an act of staggering expenditure with no clear purpose. Furthermore, the signals are not encoded with complex information. They follow the natural patterns of plasma physics. Their dispersion and polarization are perfectly explained by their journey through magnetized space, not by artificial construction. While the search for extraterrestrial intelligence remains a noble scientific endeavor, fast radio bursts have all the hallmarks of a natural, if extreme, astrophysical event. The universe, it seems, is perfectly capable of creating its own spectacular flashes without any help. Beyond speculative origins, scientists had to rule out more mundane explanations closer to home. Could these be glitches, technical artifacts from our own instruments, or interference from earthly sources? This was a serious consideration, especially after the first detection. The process of elimination was meticulous. Radio telescopes are shielded and use sophisticated software to filter out terrestrial radio frequency interference, from satellites to everyday electronics. Crucially, the telltale sign of a true fast radio burst is its dispersion measure. The signal's characteristic chirp, caused by its journey through the intergalactic medium, is nearly impossible to fake with local interference. When multiple telescopes, separated by continents, detect the same burst with the same dispersion, the case for an extraterrestrial, astrophysical origin becomes ironclad. These are not mistakes in the data, they are real events echoing across the cosmos. To understand what fast radio bursts are, it also helps to clarify what they are not. Within our own galaxy, we have long observed pulsars, the spinning neutron stars that emit regular lighthouse-like beams of radio waves. Occasionally, a pulsar will produce a giant pulse, a burst of radio emission that can be hundreds or thousands of times brighter than its usual steady pulse. These share a family resemblance with fast radio bursts. They are brief, bright, and coherent, but the comparison ends there. The most energetic pulsar giant pulse ever recorded is still tens of thousands of times weaker than a typical extragalactic fast radio burst. It is the difference between a camera flash and a supernova. The energy scales are simply incompatible. Furthermore, pulsar giant pulses repeat predictably with the star's rotation, and they originate from within our galaxy. Fast radio bursts come from vastly greater distances and, with the exception of repeaters, do not show any connection to a steady, spinning source. So while the physics of coherent emission may have similarities, the engines are fundamentally different. A pulsar is a stable, rotating magnet. A fast radio burst engine is a catastrophe. This distinction is vital. It tells us we are not just seeing a more powerful version of something we already know. We are witnessing a new class of cosmic violence operating in a league of its own. The evidence points not to a single culprit, but to a cosmic menagerie of violent engines. After years of collecting signals and tracing their origins, a compelling picture emerges, one where the universe employs multiple pathways to produce these brilliant flashes. The distinction between repeaters and one-off bursts is the most powerful clue, a fundamental fork in the road that likely separates two different families of cosmic events. For the repeating sources, the case for magnetars grows stronger with each new detection. Their ability to survive their outbursts, the direct link from our own galactic magnetar, and the periodic windows of activity that suggest binary orbits all paint a consistent portrait. These are stressed, volatile objects living on a knife's edge, their immense magnetic fields cracking and reconnecting to fire intermittent salvos into space. They are the persistent screamers capable of shouting the same name for years. Yet the cataclysmic, one-time events tell a different story. Their sheer power and solitary nature align perfectly with terminal cosmic violence. The merger of two neutron stars, the collapse of a hypermassive remnant into a black hole, or the tidal shredding of a star by a supermassive black hole are all engines that are spent in a single, glorious instant. They represent a final, irreversible transformation, a cosmic door slamming shut with a radio frequency bang. This duality suggests that fast radio bursts are not a single phenomenon, but a common final expression for several of the universe's most extreme processes. It is like hearing a loud crash in a city. It could be a car collision, a construction accident, or an explosion. The sound is similar, but the causes are vastly different. The emerging consensus among astronomers is one of a heterogeneous class, a collection of brilliant radio signatures with multiple origins. The specific properties of a burst, its energy, its host galaxy, and its repetition pattern are the clues that tell us which engine we are hearing. A faint, complex burst from a young, star-forming dwarf galaxy likely points to a young magnetar. An incredibly luminous, one-off flash from an older, quieter galaxy might be the death cry of a neutron star binary that took billions of years to finally spiral together. This framework elegantly accommodates the bewildering diversity of the data. It explains why some bursts are millions of times more energetic than others, why some repeat erratically and others never do, and why they are found in every type of galactic environment. The search for the engine, therefore, does not have a single, simple answer. Instead, it has opened a new window into the life cycles of the most exotic objects in the cosmos. We are learning that the universe has many ways to make itself heard, and sometimes the loudest voices come from engines on the very brink of existence. The next chapter of this cosmic investigation will be written by telescopes of a scale we are only beginning to build. Our current instruments have lifted the veil, but the true nature of these engines demands a deeper, clearer view. That future is arriving in the form of the Square Kilometre Array, a project that will redefine our perception of the radio sky. Imagine taking every major radio telescope on Earth and combining their collective power into a single, seamless instrument. The SKA will do exactly that, using thousands of antennas spread across 2 continents, in South Africa and Australia, to form the most sensitive radio observatory ever constructed. Its impact on the hunt for fast radio bursts will be nothing short of revolutionary. Where current telescopes detect hundreds or thousands of bursts, the SKA is expected to find tens of thousands every single year. This will transform a trickle of data into a roaring river, providing the statistical power to finally answer the most persistent questions. But it is not just about quantity, it is about quality. The SKA's incredible sensitivity and resolution will allow it to capture these bursts with exquisite detail, like switching from a grainy security camera to a high-definition slow-motion film. For the first time, we may be able to see the internal structure of a burst as it unfolds over mere microseconds, watching the shockwave propagate and the maser ignite in real time. We might even catch a burst in the very moment of its birth, seeing the immediate aftermath of a Magnetar quake or the first instance of a neutron star merger's jet. This level of detail will be the ultimate diagnostic tool, allowing scientists to directly test the predictions of every theoretical model against the raw physics of the event itself. Yet a brilliant detection is only the first step. To truly understand the engine, we need to see it in every kind of light it emits. This is where speed becomes everything. The millisecond flash of a fast radio burst is often over before our most powerful optical and X-ray telescopes even know to look. The key is a global network of instant communication, a rapid alert system that operates at the speed of light. When the SKA or another next-generation telescope detects a burst, especially a promising one from a nearby galaxy, it will need to broadcast its coordinates to the world within seconds. This automated alert will act as a cosmic starting pistol. Robotic optical telescopes on mountaintops will immediately interrupt their programs and swing toward the target. Space-based observatories like those watching for X-rays and gamma rays will reorient their sensitive instruments. The goal is to capture the fading afterglow, the heat signature of the explosion before it vanishes forever. Catching that multi-wavelength echo would be the definitive breakthrough, linking the mysterious radio scream directly to the fireball of a known astrophysical cataclysm. It would tell us the total energy of the event, the temperature of the material, and the chemical elements forged in the violence. With this coordinated, global effort, each fleeting radio whisper becomes a beacon, summoning every eye we have on the sky to witness the full story of its creation. The true prize of this cosmic hunt is not just a catalogue of distant explosions. It is a fundamental understanding of matter itself, pushed to its absolute breaking point. Fast radio bursts are far more than celestial fireworks. They are the universe's most extreme physics laboratories. Within these fleeting milliseconds, conditions are created that dwarf anything we could ever hope to replicate on Earth. We are talking about magnetic fields so powerful they can rip atoms apart, densities where atomic nuclei touch, and temperatures that make the core of our sun feel cold. This is the realm of extreme plasma physics, where the normal rules of matter break down and we must rely on the complex equations of relativity and quantum mechanics to even begin a description. By decoding the signals from these events, we are not just identifying stellar corpses, we are testing our theories about how the cosmos behaves under the most unimaginable stress. The coherent radio scream we detect is the final, distant echo of a chain reaction that begins in this exotic realm. It is the product of a relativistic shockwave, a wall of plasma moving at over 99% the speed of light, slamming into a magnetized cloud. The physics of this collision is a turbulent dance of charged particles, magnetic field lines, and intense radiation pressure, all orchestrated by the laws of electromagnetism taken to their ultimate extreme. Understanding how this chaos produces a perfectly synchronized radio beam is one of the grand challenges of modern astrophysics. It forces us to refine our models of how energy transfers in a plasma, how magnetic reconnection works at relativistic speeds, and how coherent radiation can be amplified from such a violent, disordered environment. Each burst is a unique experiment run by nature, a test of our physical theories under conditions we can only observe, never control. The results of these cosmic experiments are written in the polarization, the frequency sweep, and the fine structure of the millisecond signal. By matching our predictions to these intricate fingerprints, we can validate or discard our ideas about the fundamental behavior of matter and energy. This quest leads us to the very edge of known physics. The environments around magnetars and merging neutron stars are so dense and so magnetized that they may even allow for the formation of exotic states of matter. Could there be a soup of free quarks, the fundamental building blocks of protons and neutrons, swirling in the hypermassive remnant of a collision? Could the intense magnetic fields generate particles from pure energy, or create currents that flow without resistance? These are not just speculative questions, they are direct consequences of the physics we believe powers these engines. A fast radio burst is a brief window into this alien physics, a flash of light from a world governed by rules we are still struggling to write. Solving this mystery, therefore, is about much more than naming a new type of cosmic object. It is about advancing our comprehension of the universe's fundamental forces. It is about learning how matter behaves when gravity and magnetism win their eternal struggle against the nuclear forces that hold atoms together. Every time we catch one of these brilliant whispers from the dark, we are given a priceless glimpse into the ultimate limits of physical law, a chance to read the universe's own textbook on how to build an engine from pure energy. From a single, baffling signal in old data, a new window on the universe has been flung wide open. What began as an isolated cosmic anomaly has blossomed into an entire field of astrophysics, revealing a cosmos punctuated by brilliant millisecond screams. The journey to understand them has not led to one simple answer, but to a gallery of extreme possibilities. We have magnetars, stressed stellar corpses cracking under magnetic strain. We have neutron star mergers, the fatal, final embrace of two dense cores. We have the chaotic births of hypermassive objects and the monstrous appetites of supermassive black holes. Each candidate engine represents a different pathway to cosmic violence, a testament to the universe's boundless creativity in generating unfathomable power. This multiplicity is not a failure of science, but its greatest success, showing how a single, dazzling effect can arise from multiple profound causes. Fast radio bursts have thus fulfilled a dual role. They remain profound cosmic puzzles, their exact triggers still debated in observatories and lecture halls around the world. Yet they have also become something more, powerful new tools for exploration. Each flash is now a probe, illuminating the invisible material between galaxies and mapping magnetic fields in the cosmic voids. They are both the mystery and the flashlight we use to investigate the dark. This entire pursuit, from that first lonely day to point to the global networks hunting for counterparts, perfectly embodies the scientific process. It is a story of curiosity meeting observation, of theories being built and broken by new evidence, and of technology rising to meet a profound challenge. The drive to comprehend these flashes has pushed our understanding of physics to its limits, forcing us to contemplate matter under conditions we can scarcely describe. It reminds us that the universe is still a place of wild, energetic wonder, where the most violent engines imaginable operate in the dark, waiting only for us to learn how to listen. The story is far from over. New telescopes will soon open their eyes, bringing thousands more bursts into focus and perhaps capturing that elusive, multi-wavelength glimpse that finally settles the debate. So stay curious. The next chapter of this discovery is being written right now, in data streams from mountaintops and deserts, promising to reveal even more about the spectacular and unforgiving physics that governs our cosmos.